Hi, so differentials, that's our next topic. And I think in the previous section, I talked about the sort of total derivative, and we're going to sort of get into that here a little bit. Of course, it is a much broader topic that you can get into in more advanced courses, in advanced calculus or differential geometry or analysis. So we're only going to touch on it a little bit here, and in particular the applications of it and the usefulness of differentials. We will look at some of those as well. So depending on where you've had Calculus 1 before, you may have talked about differentials. When I teach Calc 1, I typically don't. I kind of skip that topic. So maybe we'll do a very quick, for some of you a review, and then for some of you, you may not have seen differentials before. So if you have a function of one variable, say y is a function of x, again, just from Calc 1, then you can write the derivative in two different ways, right? You can write it as the derivative of y with respect to x, right? These are not partial derivatives now. This is a regular derivative. Or you can write it as f prime of x, right? And you should be comfortable with both notations because we use both, right? So what you can do, of course, is multiply both sides by dx, and you get this, right? So we refer to the dy and the dx as differentials, right? Right? Or infinitesimals, if I can spell it, infinitesimal, right? But we're not going to get into that. After all, what do we mean when we say dx? Well, informally, if you don't take it too seriously, it's effectively the limit as delta x approaches 0 of delta x, right? Which is a little bit absurd because, well, isn't that limit just 0? And then, of course, you would think dx is 0 and dy is 0. So that's not quite the whole story here, right? Right, dx is sort of the closest thing you can get to 0 without actually being 0, if that even makes sense, right? So don't think about differentials or infinitesimals that way. We're going to treat them essentially just like we would a delta y or a delta x, right? Now, delta y and delta x could be finite changes in x, right? So delta x could be 12, right? And delta y might be 2. But for our purposes, we want the delta x and delta y to be very, very small, right? Almost 0, effectively. Okay, so yeah, let's get rid of that. Right. And so now we can go on to a function of two variables. Let's suppose z is a function of x and y, right? Then we can write dz as a differential. In fact, we can think of this as the total differential. I'll just call it the differential of z, right? So the total differential of z, or just the differential of z, is defined to be the following, right? It's the partial of z with respect to x times dx plus the partial of z with respect to y times dy, right? So this is called the total differential, or just the differential of z. So kind of similar when you have the first derivative, but you only have one term, right? And while we're at it, if we have w as a function of x, y, and z, then the differential of w is going to be, well, partial of w with respect to x times dx, plus the y partial of w times dy, plus the z partial of w times dz, and so on, right? So there you go, right? These are differentials, and they're calculated just using the partial derivatives, right? So just a quick example, right? Suppose we have W is, I don't know, how about x cubed plus y squared minus 6yz squared, right? And we want to find dw, right? The total differential of w, right? Total differential of w. Okay, well, I should use yellow here. Same idea. So what is dw? Well, by definition, right, we have to take all three partial derivatives. Right, so I'm just copying down the definition. Right. So what is the partial of w with respect to x? It's just 3x squared, right, times dx, plus now the y partial. So you're going to get 2y, but you're also going to get minus 6z squared, all times dy, right? And then the z partial. So you have 0 plus 0 minus 12yz. So negative 12yz times dz. Right, so that's dw. Right, and you just leave it like that, right? Yes, more generally, again, most of you probably are not going to see this unless you take an advanced calculus analysis course or differential geometry, in which case these are called one-forms, right? So if I ever refer to something called a differential form, right, this is an example of what's called a differential one form, or just a differential form in general. And you can have two forms and three forms, but that's way beyond what we want to do here. So this is, you know, in some of your futures if you go on to higher level mathematics. But for our purposes, we're just going to treat these as just informal symbols that represent what happens when you, right? So what happens when you change x by a little bit, what happens when you change y by a little bit, and what happens when you change z by a little bit. How does that affect w, right? When you change w, how much does that affect the change in w? So that's sort of the idea here. Yep. Oh, and maybe we should write these in the other notation here, right? So this is also just f sub x dx plus f subscript y dy, right? This is going to be fx dx plus fy dy plus fz dz, right? So yeah, either way, I tend to write it with these backwards sixes here. All right. So I think the next thing we should talk about before we do some more examples is, remember, when you have z as a function of x and y, right, we know what dz is. It's just, we'll do it this way again. Y, right? But then what is delta z? Right? So delta z is a change in z when you change both x and y. So let's take x plus delta x and y plus delta y, and then subtract the original, right, f of x, y. So this is the definition of delta z, and this is the definition of dz, and you can see they're not the same, although they could be the same in some cases, but usually not, right? So I want to spend a little time on making sure you understand the difference between dz and delta z, right? And I think that the easiest way to do that is just to look at what I hope to be a simple example. right, a rectangle. Or maybe let me draw it over here. Right. Right, so we're going to talk about the area of a rectangle. Right, we'll just call it A. And right, this is the length. We can call it L. I'm going to call it X. And then the width is usually W, but I'll call it Y. So area is a function of both X and Y. But it's a very simple function, right? Length times width, X times Y. Okay? All right. Now, what we want to do is change X a little bit. If we increase X by this amount here, I'll call it delta X, right? Right. And we increase Y by a little bit, right? I'll call this little piece here, we can call that delta Y, right? So, right, so that's what you get. And what is the new area, right? So the new area of the bigger rectangle, right? This rectangle here obviously has a slightly bigger area. Okay. So this is the area of the first rectangle, the smaller rectangle, and then the area of the larger rectangle, right, is just this. Right? So you just multiply X plus delta X, right? That's the new length, times Y plus delta Y, right? That's the new width. Make sense? Oops, I didn't mean to do that. Y plus delta Y, right? Okay. So what's the difference, right? So the change in area, the increase in area, maybe I can fill that in here. In blue, that's going to be this plus this. Oops, not that. Plus this. And then there's this little tiny rectangle in here. I'll do that in purple. So, but you know, but that's going to be part of the change. So, right. So what is that delta A? It's simply the area. Oops, the area of the small. The area of the large rectangle minus the area of the small rectangle. Right. So it's just X plus delta X times Y plus delta Y minus XY. Right. So your delta A, if we multiply this out now, you get X times Y plus X times delta Y, right, plus Y times delta X, right, plus delta X times delta Y minus XY. And XY minus XY is 0. So essentially you're canceling out, right, the area of the small rectangle, right? That's this area in red here. Okay, so when you subtract that area out, you just get the blue area plus the purple area. Okay, so when you cancel those, our delta A, delta A can now be written as X times delta X, X times delta Y plus Y times delta X, and then plus delta X times delta Y. Okay, so what is X times delta Y? It's this up here, this rectangle up here, this tiny slice of a rectangle, right? Let's see, what is, can I do Y times delta X? Yep, that's this piece right here, Y times delta X, right? And then finally, delta X times delta Y, that's just this tiny little, it looks like a square, right? But it's this tiny little rectangle here, delta X times delta Y, right? So you add up all three of these little rectangles here, and that gives you the total change in the area. The big one minus the small one. The small one being not that small. By small, I mean just the red rectangle here, right? So this one here, right? So that's what I mean by the small rectangle here, right? That's just the xy that we're subtracting off, right? So of course that's included in the big rectangle too. That's why when you subtract them, you get 0. So makes sense. Okay, so this, it's just adding up a bunch of rectangles here. That's all that is, to find delta A. Right. So now what's dA? Right. What's the differential of A? So let's calculate that. dA. So just as a reminder, it's the partial of A with respect to x times dx plus the partial of A with respect to y times dy. And remember what A is. A is just x times y. So these two partial derivatives are about as simple as it gets. The x partial is y, and the y partial is x. So all you get is y times dx plus x times dy. Okay? So in our picture again, and I'm going to run out of space pretty soon, so let me just copy it down here. Right, so here's our rectangle, right? This is x, this is y. And then let's make this dx, or delta x, either way, it's the same. So I guess I'm making it a little bit bigger here, right? And then delta y, or dy, would be this. Right. So yeah, so dA then is just going to be, I'm looking for a color here. Yeah, so let's make this one y dx. We'll make that one red here. Right. So y dx is this term here. And then in green, we have x dy. So that's going to be this term in here. Right? But that's it. Right? So that's dA. This is equal to the chain, right, the dA here. So what's the difference between dA and delta A? Well, remember the delta A includes this term here. Right? It includes this purple rectangle in the little corner here. The dA does not include that. Right? So the dA does not include this little, sorry about that. Slip of the pen here. Right? It does not include this little piece here. So this is not included in dA. So that's the only difference, right? Right. And effectively, this tiny rectangle here, this piece up here, is so small that it can, for all practical purposes, it can be neglected, right? It can be ignored without too much difficulty, right? Without too much of an error, right? So the dA is essentially just an approximation, right? You can think of the dA, right? It's really just delta A minus the delta x times delta y. But since delta x times delta y is very small, we can effectively ignore it, and it's very approximately equal to delta A. It's pretty close. Okay, so that's the difference between delta A and dA. Right? So effectively, we're thinking of the dz here, right, as an approximation to delta z. They're not exactly the same, but right, you're just missing that little corner here when you do dz. Okay? So yeah, the delta x, delta y is sometimes referred to as a second order term. Right? These two being first order. Right? Because they only contain one delta, right? If it contains two deltas, it's a second order. If it contains three deltas, like if you have delta x, delta y, delta z, this would be considered a third order term, and so on. Right, so the differentials ignore anything other than first order, right, ignoring second order and higher order terms. Okay, so I hope that at least gives you some perspective here about the difference between the dA and the delta A. So that's the same thing between dz and delta z. They're not exactly the same, but they are approximately the same, right? Effectively, the dz is what's called the linear approximation. It's the linearization, right? So this is the linear approximation of delta z, right? Or the linearization. Okay, so I hope that helps. Okay, so we're going to get a little bit technical here. This is, a bit analytic, but in the last section we talked about partial derivatives, and we never really mentioned when is a function of two variables, say x and y, when is it differentiable, right? Because in Calc 1, you remember a function is differentiable if its derivative exists. And so you might think that a function of two variables is differentiable when the two partial derivatives exist. And unfortunately, it's not quite that simple. So this is where it's going to get a little bit technical, but I think it's worth doing, again, especially for those of you going on to analysis. So a function of two variables is differentiable, and let's say at a specific point, let's say x0, y0, right? And then we can talk about a function being differentiable at a whole bunch of points or in its entire domain. But for now, it's just differentiable at a point, right? If we can write delta z, right, the following way. If we can write delta z as the partial derivative of f with respect to x, evaluated at x0 and y0, right, times delta x, right, plus the partial of f with respect to y times x0, y0, right, times delta y, right, plus some correction factors, right, epsilon 1 times delta x plus epsilon 2 times delta y, right, where in particular these epsilon 1 goes to 0, and epsilon 2 goes to 0, right, as delta x and delta y both go to 0. Okay, so again, seems like a very awkward definition, right? And it's one that, you can study for hours and still have a little trouble with it. But I wouldn't waste a whole lot of time on it. We're gonna do maybe one example and show, a function that is differentiable just by using this weird definition here, right? So just remember what delta z is defined to be, right? So what I'm writing is what delta z is if your function is differentiable. Ordinarily, delta z is just the following, right? It's f of x plus delta x, y plus delta y, minus, right, f of x, y. Right? So that's the definition of delta z. However, if you can write delta z in this form, right, and you can't always do that. If a function is not differentiable, then you won't be able to write it this way, right? But if it is differentiable, you can write it either way. Okay, right. So as an example, all right, let's show that the function, again, we can use z as a function of x and y. Let's just do x squared times y plus x. We want to show that this is differentiable. Okay. So let's start by calculating delta z. In fact, let's do that. Oops, differentiable. Let's do that here. So delta z, by definition, it's just f of x plus delta x, y plus delta y, minus f of x, y. Right. This is going to be kind of a tedious calculation, but let's go through it, right? Changing all the x's to delta x, x plus delta x, we get x plus delta x squared times y plus delta y, right? Minus the original function is just x squared y plus x. Okay, so now we're going to have to multiply all this out. And let's go step by step here. We get x squared plus 2x delta x plus delta x squared, right? And then times y plus delta y minus x squared y minus x. And now we multiply all this out. We're going to get x squared y, right, plus, let's do it this way, x squared times delta y, and then plus 2xy delta x, then 2x delta y, delta x delta y, right, and then y times delta x squared plus delta x squared times delta y, and then minus x squared y minus x. All right. So I think the only thing that cancels here is this first term, x squared y minus x squared y. Yep. So I think that's it. Now I'm looking, I think I forgot something here. Yeah, I forgot the plus x, right? So that, yeah. So there should also be a plus, right? For this term up here, there should be a plus x plus delta x, right? And so when you add x, that cancels the x, and then you also have a plus delta x. So I did forget those, and so these also cancel. All right, so now I think that's everything. Yeah, same thing here, right? So there should be a plus x plus delta x. That should have gone over here. All right, better late than never. All right, so again, our delta z now is going to be, and let's see if we can collect terms with the same delta. Let's do delta x first. So you're going to get 2xy plus 1 times delta x. Right, so that came from this term plus this term, just to keep track of everything. And then with respect to delta y, we have x squared. Is that it? Yeah, I think that's it. Just x squared times delta y. Right, so that's this term here. Okay. What else do we have? So let's see, we want epsilon 1 times delta x. So what are we going to have times delta x? So we have a 2x times delta y plus a y times delta x. And then we'll save this term for the delta y here, right? So this is all times delta x. So where did that come from? That came from this term here and this term here, I think. Right. And then finally, yep, delta x squared times delta y. Oh, yeah, this came from here. And then I'm running out of colors, so how about green? That's that term there. And everything I circled in red cancels, right? Okay, I think that should do it. All right, so now, so that's delta z, and now what's dz? Or what are the partial derivatives, right? The partial derivative with respect to x, which is dz by dx. So I think we just get, right, so go back up here now, take the derivative with respect to x, treat y as a constant. You get 2xy plus 1, right? And then with respect to y, you get partial of y with respect to z. Now x is a constant, so we just get x squared. And that should do it, right? So, right, so I move these down to show you, right, that this is the same as this, right? So this is just the x partial of f times delta x, right, plus, and then the x squared is this factor here, right? So this is just the y partial of f times delta y, plus, and now I have epsilon 1 times delta x. This is my epsilon 1 here, right? Plus epsilon 2 times delta y, where this is my epsilon 2. Sorry, a little sloppy there, epsilon 2. And now all we have to do is check, we take the limit of epsilon 1 as delta x and delta y go to 0. So if we take that limit, what's epsilon 1? It's just 2x delta y plus y delta x. However, delta y is going to 0, delta x is going to 0. We just get 0 plus 0 is 0. Right? And also, let's check the same thing for epsilon 2. Well, epsilon 2 is just delta x squared. So 0 squared is 0. So that satisfies this definition up here, right? Epsilon 1 and epsilon 2 both go to 0 as delta x and delta y go to 0. So that's what happens here. Right? So now we know for sure that this is differentiable because it satisfies the definition of differentiable. We got the correct epsilon 1 and epsilon 2. They both go to 0, and we got the partial derivatives worked out okay. Right. So yeah, again, kind of a confusing notion of differentiable, right? Unfortunately, this is the definition, and we have to work with it in some cases. Luckily, though, there's a better way to think of it, and that's this property here. This theorem, if you have z as a function of x and y, and both partial derivatives, right, are continuous on an open region R, then you can say f is differentiable on that region. Okay, so that way you don't have to go through all this mess here that we just did. So this is the nice shortcut here, right? So in our example, it was f of xy equals x squared y plus x. If we just take the two partial derivatives, first with respect to x, we just get 2xy plus 1. And then with respect to y, we just get x squared. Well, these should be familiar to you, right? These definitely are continuous functions, right? They have to be continuous. And they are, which means this function f is differentiable. See how much easier that was than going through all this mess up here using the definition. Okay. Well, two things. First, we didn't prove this theorem, so we didn't prove that this is true. And And we're not going to. It's the proof is probably somewhere in the book or maybe the back of the book. If you're that curious, you can take a look, and you can ask me questions later. But I don't think it's worth going into, right? The one thing you have to be careful of, though, is that you can't just say that, right, f is differentiable if the partial derivatives exist, right? Right, because remember, in Calc 1, a function is differentiable if you can take its derivative, right? If the derivative exists, it's differentiable, and that's it, right? We did not need the derivative to be continuous, although it usually is, but it doesn't have to be, right? So, yeah, this is not going to work for a function of two variables. So it's a little bit stronger. The two partial derivatives here have to be continuous, right? Which means if they're continuous, they exist. But they could exist and not be continuous. Okay, so if the two partial derivatives are not necessarily continuous, then we cannot conclude that it's differentiable. Right? In which case, you might just have to go back and use these epsilon 1s, epsilon 2s, as much of a nuisance as that is. All right. Sorry about that. Well, again, very technical, analytical ideas here. But, you know, when I say a function is differentiable, I basically just means that the partial derivatives not only exist, but they're actually much nicer than that. They're continuous. And they could even be differentiable, in which case you can take the second derivatives, and then the second partial derivatives will have to be continuous, and so on. However, what is true is if you're differentiable, then you're definitely continuous. And that was true in Calculus 1. And it's also true here. So if z as a function of x and y is differentiable, and this could be differentiable at a point or differentiable on a region. So let's just start with differentiable at a specific point. Then for sure the function is continuous at that same point or in that same region. Right? So you can be, right, if you're differentiable, you're continuous for sure. If you're continuous, you may or may not be differentiable. All right. Anyways, well, if you're curious, I can show you an example where you have a function, right, where the partial derivatives exist, but they're not continuous. So maybe let's do that. And if you're not curious, you can just end the video here. Well, actually, yeah, don't end the video. Let's do some examples. Yeah, let's do some examples first. And then I'll show you the function that has partial derivatives that exist but are not continuous. How's that? All right, let's do some examples. Okay, so here's one I just took directly out of the book. So the centripetal acceleration of a particle that moves in a circle is given by, well, it's right. So we talked about this in the last chapter, that the centripetal acceleration is v squared over r. V is the velocity and r is the radius, right? So something moving in a circle at a certain speed with a certain radius, then you can calculate its centripetal acceleration, right? So approximate the maximum percent error in measuring the acceleration due to errors of 3% in the velocity and 2% in the radius. Okay, so percent error, right? So percent error, also called the relative error, right? As opposed to the actual error, or what's sometimes called the propagated error, right? The propagated error is just the dz, right? Which in terms of x and y, if you have a function of x and y, is just the usual differential. Okay, but the percent error is dz divided by the original function z. Okay, all right. So here, because they're talking about percent errors, we're going to use this, right? Right. So what do we need? Well, we need dA first, and then we'll divide by a. So it might be helpful to think of this a as just r to the negative 1 times v to the positive 2, right? So partial of a with respect to r times dr plus partial of a with respect to v times dv. Right? In this case, the partial of a with respect to r is just negative r to the negative 2, right? So negative v squared over r squared times dr. And then with respect to v, you just get 2v divided by r, right, times dv. Okay, so that's the propagated error for the acceleration. That should be an a here. Right, so now for the relative error or percent error in the acceleration, you take dA divided by a, right? So let's think of that as just 1 over a times dA, where 1 over a is r over v squared, times, well, negative v squared over r squared times dr, plus 2v over r times dv. So when you multiply all this out here, you get that dA divided by a, that should be an a, that should be an a. What do you get? You get negative, well, v squared over, I'll write it out, v squared r over v squared r squared times dr, and then plus 2vr over v squared r dv, but we can definitely simplify that to negative, let's see, 1 over r times dr, so dr over r, right, plus, see, the v's cancel, one of the v's cancels, the r's cancel, so we just get 2 times dv over v, right, and that's it, right? So this is the percent error in the acceleration, right? So what are we given? We're given that the percent error in the velocity is 3%, right? So percent error in velocity, dv over v, is 3%. I'll write it as a decimal, right? So this was given, right? And then in r, it was 2%. So dr over r is 2%, 0.02, right? Oh, and keep in mind that, right, 3% error could be above or below. So these are plus or minus, right? These are, yeah, we should think of these as plus or minus here, right? Okay, good enough. So now the question is asking for the maximum percent error in A. So we want to find the maximum percent error in the acceleration. Oh, just have enough space to do this, right? So we have negative dr over r. We know what that is. That's just plus or minus 0.02. Forget plus or minus. 0.02 plus 2 times dv over v, that's this, plus or minus 0.03. Right, and that's a plus in the middle here. So when do we get the maximum percent error? So if they're both pluses, you get negative 0.2 plus 0.06, which is 0.04. But that's not the maximum percent error, right? If you use the minus sign here, you get a negative of a negative, you get positive 0.02. and then use the positive here to get positive 0.06, that gives you 0.08, right? Or 8%. Okay, so this is the maximum percent error. I want to make sure I got the, 3% in v. Yep, this is the maximum percent error in the acceleration. Okay. Yep, so a 2% error in the radius and a 3% error in the velocity can cause up to an 8% error in the acceleration, right? And now you can see why this is called the propagated error, right? When you propagate a small error in x and a small error in y could lead to a bigger error in z. So in this case, a small error in r and a small error in v leads to a bigger error in a, the acceleration. Okay, so yeah, this is a good example. So keep that in mind. If they ask for the propagated error, they're just asking for the differential. If they're asking for the percent or relative error, then you have to divide by the original function, which we did down here. We divided by a, right? Okay, so I hope that helps. Right, and here's another one for you electrical engineers out there, or anybody taking physics too. This is going to be familiar to you when you have a circuit with two resistors in parallel. So you have your circuit, you have your battery, your voltage, electromotive force, whatever you want to call it. And then you have a resistor over here, say R1, and then a resistor over here, say R2. They're probably different, right? These are in parallel, which means if you want the net resistance, the total resistance, right, you're using this formula here, right? The reciprocal of the resistance is the sum of the reciprocals of the two individual resistances. And so the question is to approximate the change in R. So we want the change in R, right? We can just use dr, right, for that. We don't have to find delta R. We're just going to approximate, right? So this will be approximately the true change in R. As R1 increases, right, from 10 ohms to 10.5 ohms, right? So your dr1 is an increase in 0.5 ohms, right? So these are not relative or percent errors. These are actual errors here. And R2 is decreased from 15 ohms down to 13 ohms. So that's a change in R2 that's negative, I was going to say 0.2, but it's negative 2 ohms. So this omega symbol is the symbol for ohms. I know that they spell it out, OHM, but I'm just so used to doing this. Sorry about that. So yeah, so this symbol here is the symbol for an ohm. All right, so how do we find dr? Well, one way is just to use the definition of the differential, right? So this is the partial of r. Now notice the two variables here are R1 and R2. So, yep, you might have to get used to that these are not constants now. These resistances are changing, right? They're increasing or decreasing, right? Right. So this is probably the most direct way to do it, is just to calculate these partial derivatives and do it that way. Yeah, why don't we just go ahead and do that, right? So so you can solve for R in terms of R1 and R2. I don't know. For some reason I just feel like doing it directly, right? So if you, yeah, I don't know if you're gonna like me doing it directly. Okay, so let's solve for R. Let's just flip everything over, right? So R is going to be, So please don't make this mistake. It's not R1 plus R2, right? You cannot just take the reciprocal of the sum and expect it to be the sum of the reciprocals, right? So that would be for a circuit in series when you have, R1 and R2 in series. So that would be a series circuit, but here they're definitely in parallel. That's what the question says. So R is really 1 over R1 plus 1 over R2. And you can simplify that just by multiplying by the product, R1 times R2. Right? So when you do that, R is just going to be R1 times R2 divided by R1 plus R2. And it would have been nice if they gave that to us, but again, it's just a little bit of algebra, not a big deal, I hope. So now in this form, we can just take the two partial derivatives, right? So what's the partial of R with respect to R1? So it's a quotient, so we'll use the quotient rule. So denominator times the derivative of the numerator. The derivative of the numerator is just R2 minus numerator times the derivative of the denominator, which is just 1. So I think we end up with R1 R2 plus R2 squared minus R1 R2. So those cancel. And I think we just get R2 squared divided by R1 plus R2 squared, also squared, right? And then the partial with respect to R2. Oh, sorry, R with respect to R2. So I think you can see the symmetry here, right? You're just going to get the same thing, but R1 squared. If you don't believe me, let's work it out. R1 plus R2 times R1 minus R1 R2 times 1 all over R1 plus R2 squared. So sure enough, you're just going to get R1 squared, R1 squared plus R1 R2 minus R1 R2. Right. Which means, right, these things cancel. And these things cancel here. So R1 squared divided by R1 plus R2 squared. All right, and now we can find dr itself. Right, so it's up here. I'm just going to apply the first derivative with respect to R1. You get R2 squared over R1 plus R2 squared times dr1 plus and R1 squared divided by R1 plus R2 squared times dr2. And now, let's see, we need the values here. So I'm going to just run out of space here. All right, so let me see if I can copy these. Okay, so just so that we can refer to those. And now, just plug in the numbers. So what is R2? R2 is 15 squared. And R1 plus R2 is 10 plus 15. So that's 25, also squared. And dr is 0.5. We know everything here is in ohms, right? Plus R1 squared, that's 10 squared, divided by 25 squared. And then R2 is negative 2. dr2 is negative 2, right? Yeah. All right, so just throw all this in a calculator at this point. All right, so I think 15 over 25 is 0.6. So 0.6 squared is 0.36 times 0.5 plus 10 over 25 is 0.4. 0.4 squared is 0.16 times negative 2. All right. Minus I get negative 0.12 right? Or if you prefer, negative 3 over 25. Right, so this is in ohms. I forgot the units, ohms here. Yeah. And I guess I did something wrong. All right. 15 over 25 is definitely 0.6. 0.6 squared is 0.36. And then half of that is 0.18. All right. Get this. This is 0.18 and then minus 0.32. So 0.18 minus 0.32 is negative 0.14. Okay. All right, so negative 0.14 ohms, or negative 7 over 50 ohms. Right. So these are not percents, right? This is the actual change, or, well, it's the approximate change in the resistance that you get when you increase R1 by 0.5 ohms and decrease R2 by 2 ohms. So I think that's it. All right. And, you know, the key word here is approximate, right? We're approximating, oops, I cut that off, using differentials. And I think on the test I'll make that much more clear that you're using differentials here to calculate the approximate change in the resistance, right? Because I think we can calculate the actual change much more simply. So what is the actual change in R? Right. Due to these changes here, right? So, right. So remember what R is. R is R1, R2 divided by R1 plus R2, right? Right. So, right. So what is it? What is the resistance before the change, right? So we're essentially just calculating delta R here. So this is R initial minus R final. Or actually, we want to go the other way, right? R final minus R initial. Right. So the final resistance is, let's see, R1 is 10.5 and R2 is 13. So we're going to get 10.5 times 13 divided by 10.5 plus 13, and then minus the initial, where R1 is 10 and R2 is 15. So this is 10 times 15 divided by 10 plus 15. And again, throw all this in your calculator. And let me see if I can do it right this time. So 10.5 times 13, right, divided by, it looks like 23.5. And I get some horrible fraction here. 273 divided by 47. And then this, I think, is just 150 divided by 25, which is 6. So 273 divided by 47 minus 6 is approximately, or it's exactly negative 9 over 47, but it's approximately negative 0.191489, good enough, ohms. I forgot ohms here, yeah. So that's the actual change, right? So you can see the approximate change was the negative 0.14. So this is approximate, right? And then this is, well, at least the negative 9 over 47, that's the exact, right? And here we're just approximating the fraction, of course. Negative 9 over 47 is, it's a rational number. We could get, we could use repeating decimals here, but yeah, so negative 0.14 versus negative 0.19. So you can see they're not exactly the same. So by using differentials like this, of course, you are just getting the approximate change in R. And some of you are probably wondering, isn't it easier just to get the actual change, right? Final minus initial, that was pretty quick, right? If the approximate, if we're only getting an approximate by doing this horrible, derivatives, differentials, and all that stuff, why bother just getting the approximate? And that's a good question, and I don't really have a great answer for it. All I can say is that in some cases, you want to sort of do a linearization procedure and just get the approximate error using the tangent plane as an approximation, right? As opposed to the actual error here. So yeah, and in fact, we could have done this in the previous example using the acceleration. We could have found the actual percent error versus the approximate percent error using differentials. So the actual change in R does not use differentials. It just, do final minus initial. But the approximate uses differentials, and yes, you need to get used to that. Because on a test, I will very much likely ask you, find the approximate error or approximate change in a quantity, right? And I will specifically say using differentials. I know the book doesn't make that perfectly clear. However, the whole section is on differentials, and so it's giving you a clue there that you should be using differentials, right? Don't take the shortcut and do it the simple way here to get the actual change. Okay, so I hope that helps. Now, right, we can end the video here, or if you're curious about that function that whose partial derivatives exist but are not continuous, let's do that now. Okay, so at this point, let's consider this example optional. I think it's in the book. I think it's one of the examples in the book. So I'm just going to go through that one a little more carefully maybe. So here we have a function of x and y, right? And I think we've seen it before, xy divided by x squared plus y squared. As long as x and y is not the origin, right? Because notice that this is obviously undefined when x and y are both 0. So this is not defined at the origin, but we're going to define it to be 0 at the origin, right? So we want to show that this is not differentiable at the origin, even though the two partial derivatives exist. Okay. So let's start with the partial derivatives, right? What is the partial derivative of x evaluated at 0, 0? Well, the problem is the way that the definition works here, right? The function is defined to be 0, but what happens when you're close to 0? And in what direction, right? So the easiest way to do this, rather than try to take the partial derivatives of this, right? Let's just use the definition, right? Take the limit as delta x goes to 0 of f of 0 plus delta x, 0, minus f of 0, 0, all divided by delta x. Right. So in this case, I don't think this is that difficult because you're just changing x to delta x, and you're leaving y as 0. Sorry, that's an x. So what do we get? Well, so we get delta x, right, times 0 divided by delta x squared, right, minus f of 0, 0 is 0, divided by delta x. So what I think we get is, well, just 0 minus 0 divided by delta x, right, which is 0. Oh, I forgot to write the limit here. Oops, my bad. But you're taking the limit of 0, right, which is, sorry about that, which is 0. Okay, so the x partial derivative exists, it's just 0. And same thing for the y partial derivative, all right? Now it's just the reverse. You're taking the limit as delta y goes to 0 of f of 0, and then delta y minus f of 0, 0 over delta y. So you take the limit as delta y goes to 0 of, so 0 times delta y, which of course is 0, divided by delta y squared. minus 0 divided by delta y. So this is still the limit as delta y goes to 0 of 0 minus 0 over delta y, which of course is 0. So yeah, both the x partial derivative exists and the y partial derivative exists, and by coincidence they happen to be the same number. They're both 0, right? So yep, these partial derivatives exist, right? But then why is it not differentiable? Well, right, this function f is not even continuous. It's not continuous at 0, 0. Right? And I think we showed that in the previous video, or yeah, the previous one, or I think when we talked about limits. So that was in section 13.2. We talked about continuity there, and yeah, I think this is the example where we showed it's not continuous because it depends on which direction you go in. It depends on their theta. So if you switch to polar coordinates, right, if you write this in terms of r and theta, I think you just get, I think it was sine of 2 theta or something like that. Yeah, or 1/2 of that, right? Sine theta times cosine theta. Right. But that will vary as theta varies, in which case you don't get the same thing approaching 0 from any direction. You get different values. Right. So this is not continuous. And if it's not continuous, it's not differentiable. Okay. So this function is not differentiable, even though we can take both partial derivatives, right? Because the issue is that the function is not continuous, right? And so neither are their partial derivatives. So even though we can take their partial derivatives, these are not continuous functions, at least not at 0, 0, right? Not at the origin, right? They may be continuous everywhere else, just not at 0, 0. But that's exactly where we want to show it's not differentiable. All right. So if you didn't follow that, don't worry about it. It's kind of a technical analytical point. But for those of you interested in mathematics, this might be the fun part of math. At least it was for me. But I recognize that most of you want applications, and you want to see where is this useful in physics, engineering, and all that. So those were the previous examples we talked about. So that should do it for this section. In the next section, we'll get onto the chain rule, I think.